What is the midpoint of the line segment joining the points -1, 3, 9, and 5, 6, -3? What do you have to do to find a midpoint? Average, yeah. Remember, I think I told you that when we're dealing in 3 dimensions, sometimes it's going to be something different. Tina? Something wrong? We'll just finish this one, sure. This one's just going to be -1 plus 5 over 2, 3 plus 6 over 2, and 9 plus -3 over 2. Okay? Yeah, okay. Yeah, I think plane. So, which one's the YZ plane? It's going to be this one right here.
It's the wall.
It's the wall that you're facing from our perspective, yep. So you're at the point -1, so you go back, so x goes back -1 like this, and then what do you do?
3 to the left.
3 to the left, and then what do you do?
3 down.
Down, so you're down kind of in that back, lower quadrant, back left. So that's where you are right now. Nice, okay. You walk 2 units forward. So if you go 2 units forward, what is that going to mean if you're going towards the Y, if you're going towards the YZ plane, if you go forward?
You'll go to the
X-axis, so that's going to turn it in 2 units forward, is going to bring you to 1, -3, -3. Correct? Turn left and walk 2 units. So if you go to the left now, you're going to be facing the XZ plane. So you walk this way, you walk like towards us. Going to the left, we go to the XZ plane, so that what value do you increase? The X, Y, or Z value now? The Y value, right. So you have 1, -1, -3. And walk 2 units to the left and turn. You walked 2 units forward, turn left, walk 2 units. What is your final position? Right there. It's all the points where Y is equal to 3. Mm-hmm.
Okay, so that's
correct. It's perpendicular to the y-axis. You see the point here? You see this point right here? That's the point where the plane intersects the y-axis. Is it perpendicular to the y-axis? Yeah. Perpendicularity, it just needs to be 90 degrees all the way around like that. And in this case, the y-axis is coming straight to the right. I changed the perspective there, so I'll erase it. Does that kind of make sense? Mm-hmm. This is a sphere. That's correct. And it's asking for find the equation of the circles, if any, where the spheres intersect each coordinate plane. Well, the XZ plane is when what is 0?
Y.
When Y is 0, exactly. So what do you do?
Find if there are any points in space where Y equals 0.
Yeah, so what do you do?
Draw this.
No drawing here.
Substitute X.
No X, no. XZ plane is when Y is 0, so what do you do?
Substitute -3 as well?
No, so this is 0.
It's literally right there in front of you. It's literally right there in front of you. So what do you plug into what? 0 for Y. Yeah, okay, it's right there. Right there, no trick. So we have X minus 1 squared plus 9 plus Z minus 2 squared equals 4. And then you keep on doing some math, and what do you end up with? What is that?
Circle.
No, it's not. It's impossible. That's a problem, kids. Why is that a problem?
2 squared.
Yeah, this is positive, this is positive, and this is negative. So what does this tell you? Does not touch XZ plane. So then you do it for the other 2 planes.
Okay.
That's all you do.
Oh, okay.
Does that make sense?
Yeah.
Yeah. 2 variables, 2 inputs, 1 output. We looked at it on Friday. I showed you that temperature map that didn't make sense to most of you because you live in a world of Celsius, so it didn't make sense. Once I told you it's Fahrenheit, it made a little bit more sense. But the idea is you're plugging in an X and a Y and you're getting out a Z value. You're plugging in an X and a Y and you're getting out a Z value. So Ali, for example, let's say I asked everybody, but Ali especially, if I asked you to make a graph of f of xy equals x squared plus y squared, let's say I asked you to graph that, how would you go about graphing that? What might you want to make?
Table.
Make a table. And in this case, it's not just going to be 2 columns. What is it going to be? Or it could be 3. Yeah, you could do x, y. Sure. You absolutely could make it 3 columns. You could do x, y, and z. The challenge is, instead, when we were in 2 dimensions, you plugged in a lot of x values. Like these were all x values, and what did you do at each of these x values? You got a height of some kind, right? And then you made the graph. Maybe it was a parabola, maybe it wasn't. The idea here, though, is instead of going from the x-axis to a height, You're plugging in an x and a y value. You're plugging in a plane of values. So this, let's say this is the origin right here. So this is the x-axis and this is the y-axis. At each of these lattice points, what are you going to need to find? A value, exactly. So at each of these points, you need to find a certain height. So instead of doing it in 3 columns, it might be nice to do what instead? Any ideas? So instead of doing x, y, and z, so what we propose we do x, y, z. Yeah, exactly. I like that. So instead what you do is you do x and y. So you have, like, maybe let's say 0, 1, 2, 3, 4, 5, and then you have y at x as 0, 1, 2, 3. So what point does this represent? What value do I plug in there if this is the function z equals x squared plus y squared? Yeah, y is at 0? So then it's going to be 1 and then what? 4 and then 9, 25. But then down here, what is it going to be? It's going to be 1, 4, 9. But then it gets more interesting once you start filling in the other parts of the grid, right? So we get 1 squared plus 1 squared is 2. And then you get 5, 10, 17, 26. And then what do you get? You get 2, oh, you get 4, 9. You kind of, this thing, is there going to be some symmetry in this graph? Is there going to be some symmetry in it? Yeah, absolutely. 2 squared plus 2 squared is? Where's it 10? Oh, is it?
5 and 10.
Oh, sorry, I copied the wrong line. It is 5 and 10. Thank you. So then you get 2 squared plus 2 squared is? Wait, 2 squared plus 2 squared is what?
8.
8. 3 squared plus 2 squared? 13. So can you keep on filling these in? Absolutely. Now, once you have these values, what do you do with these values? Start plotting them, right? You start plotting them. Now, if you plot them with different degrees of density, what we did is right here. This is what we graphed right here. We graphed each of these individual points, and this is kind of like doing line segments to trace a parabola. To get the smoothness of the parabola, we need to graph more and more points. So the more points you graph, the smoother it gets. So what does this look like right here? If you had to describe it in words, what would you describe that general shape as? A bowl. Yeah, that's a good general word right now. We're going to have more precise words? Absolutely. Now here's the thing. Are you generally going to be expected to graph it like this, like graph points and then plot each individual point? No. Is it going to get really, really messy if you graph individual points like that? Yeah, it really, really is. So instead, we need to learn how to understand what the general, so if this is the general shape right here, how do we transmute certain fixed shapes? What I mean by that is, what's the only change between what we just graphed? So we before had x squared plus y squared. What happens when you graph this one? It moves. Which direction, how much? What the general movement looks like. Now, are these rules pretty similar to what you've done before? Yeah. Ali. To graph these three-dimensional functions. So what you can do instead, is this shape the exact same one we were dealing with before? Yeah, it's x squared plus y squared. What you can do instead, fix a value of z, x, or y. Fix a value, and what will you get? So for example, let's say I fixed one of these values right over here. Let's fix it right here. Let me zoom in. Do you see that plane that's drawn right there? That plane is which plane? That light blue one. What plane is that? What plane is it? It's the YZ plane. Does everybody see that? That's the YZ plane. It's one of like the axial planes. What is the equation for that plane? What's the equation for that plane? That's all the points where this is x equals what? What? No, that's what's up in there, which has nothing to do with what I'm drawing right now. 0. If that is the definition of the YZ plane is when x is equal to what? 0. Okay, so what was the equation we're dealing with? We're dealing with z equals what? Equals x squared plus. So when x equals 0, what does z equal?
Y squared.
Y squared. What does the equation look like? Z equals y squared. Oh, do you see that blue line right there? This is on our three-dimensional shape, but this is only one trace. This is one trace right here, one trace of it. So we have that one parabola right there. But what can we keep doing?
Keep on tracing.
We can have more traces, exactly. We can have more cross sections. We could have more cross sections. So for example, instead of x equals 0, what could we have? X equals 2, x equals 3. And what are we going to get for traces? What is x equals 2 going to look like? It's going to be like right there. What about x equals 3? It's going to be right there. Can you see I'm trying to draw that on? So do you see the circle right here? Do you see the parabola? I'm trying to draw that on the outside of it. Now here's the thing. Is it kind of hard to see the perspective on that? So drawing successive parallel traces can be helpful, but it might be nice to have what other traces, what other contours might it be nice to have? Fixing other what?
Variables.
Fixing other variables, exactly. So let's look at this one again. Let's fix a different variable. What's perpendicular? What is perpendicular to the YZ plane? What's perpendicular? Which axial plane is what? The XZ plane. The XZ plane. This plane right here. Does everybody see that plane right there? That plane is perpendicular to the YZ plane. So what are we going to do? Well, if we used the XZ plane, what's the equation for the XZ plane? That's when what is 0? That's when y is 0. So we had z equals x squared plus what? X squared plus y squared. Yeah, so what is z going to be equal to? What does that graph look like? Well, it starts at the origin here, and what does it do? It goes up like this, and it goes on the other side like that. The point is, if you just had those two traces, I'm going to draw them off to the side here. If you just had those two traces, do you have a lot of information? Yeah, you do. Here's the first trace we had. Let me draw this. What's the equation of this one right here, this red one? That is z equals what?
Y squared.
Y squared. And then, if we had another one, let's say it's blue, what's this one? Z equals x squared. Well, you know this is a smooth surface. You know this is a smooth surface, so can you start connecting them? Exactly. So, what does this actually look like? You could take it, and you could, and what do you get? What shape did we, what was our general name for that shape? A bowl. A paraboloid. Exactly, this is a paraboloid. That's the precise name. But the point is, did we have to draw all those dots in and then connect them? No. Please don't do that. This is called, I think the technical name for this right here is a wireframe right here. Are you ever going to have to make those by hand? No. I'm not going to make you make, maybe one day, but not right now. Okay, so Ali, you asked about this one right here. X squared minus y squared. You could, if you were totally lost, you could make a table of values, right? And again, sometimes that might be helpful if you have no idea what it looks like. But instead of doing, let's do what we just did. So we have z equals x squared plus y squared. So let's say we wanted to know what does it look like on the xz plane. The xz plane is when what is 0? When y is 0. So that's going to be z is equal to what? Oh, it's minus, by the way, sorry. Minus. Is that kind of different? So z is going to be equal to what? X squared. Nice. Now what about the yz plane? That's when x is 0. So what's that going to look like? Negative y squared. So if we graph this really nicely, and I'll do my best here. Let's do this right here. I'll do it right there. There we go. It's kind of interesting when you start thinking about it. So the xz plane, so here's z, here's x, and here's y. We have z equals x squared. So what do we end up with? We end up with kind of like this right here. That's on the xz plane. It's kind of going this way, right? So what does the other one look like, though? It looks like this, right? So what does this surface look like, everybody? What does it look like? Well, here's a fun thing to think about. Let's say you're standing at this point right here. Let's say you're standing at the origin. And let's say you're standing with your arms out like this on the x-axis. What kind of concavity is this? That's concave up. Well, let's say I turn this way, parallel to the y-axis. What concavity do I have? Concave down. So that's a single point. It's a continuous function. What kind of concavity does it have? It's concave up and it's concave down. This is my favorite surface that we will, this is my favorite surface, is period. Does anybody know what this is called? Hyperbolic paraboloid. This is an awesome, awesome, awesome shape that we will think about. It's a fantastic shape. Love it. Example, you can try sketching it. Kind of like keeps going down like this, right?
So it's like a tunnel.
But then does it go, where does it go up? You know, you have to be really, really, really careful, right? Because at some point it also is going what? It's also going up as well. So it's going up like this, but it's going down like that. So there's like a ridge of some kind, but it's not, there's no kink in it. There's no like absolute value point. It is totally okay if you can't see this right now. Now, what did I say? You're not going to do these by hand, but what can the magic of the internet and the computer do for you? Calculators can, but you also have, Wolfram Alpha does these really nicely. Really nicely. So this is z equals x squared plus y squared. And then if you get, like, I think if you pay, you can start manipulating this one right here, but it's an infinite paraboloid. Now, what was that one change we wanted to make to this? So instead of plus, let's turn it into minus. So look what happens. Ready? Oh. Bing. Take a look. Let's see if it does it. There it is. See that shape right there? Here's what it looks like. Hyperbolic paraboloid.
So
Kind of cool, huh?
every point concave up every
Is every point?
Yeah.
That's a really good question. Let's take a look. Look at what we're seeing right here. Take a look. Let's just pick a random point here. If you pick, let's say, this point right here, you see that one? In this axis, what is it doing? Is that concave up or down? That's down, right? But then, if you go perpendicular to it, what do you see? Up. So it kind of looks like that every point is concave up and concave down. Pretty cool, huh? It's called the saddle. I know. So let's draw where they intersect the xy, xz, and yz planes. So the xz plane, that's when what value is 0? That's when what?
Oh, no, sorry.
Y is 0. So what's that going to be? Z equals 1 plus x. So what about the yz plane? What's that? That's when what? X is 0, right? So therefore z is equal to 1 minus what? Y. And then what about what's the last plane? The xy plane, if you wanted to do it, which you can. That's when z is what? 0. So that's when 0 equals 1 plus x minus y. What are all of these? If you graph those on a plane. If you graph those on a single plane, what are they?
Line.
They're lines. They're linear, exactly. So what do? You graph these 3 lines. You graph these 3 lines in 3 space. You graph each one. So let's do the first one. This is the z, this is the x, and this is the y. So 1 plus, let's do this one right here. I'll do this one in red. Z equals 1 plus x. When z is 0, what's x? When z is 0, what is x? What? Negative 1, right? Right there. And when x is 0, what's z? When x is 0, what's z? 1. So this is a line. So what does this line look like? Looks like this, right? Correct? It goes up and then down below. You with me so far? And that is on the xz plane. Let's do z equals 1 minus y. Let's do that in green. When y is equal to 0, what is z? When y is equal to 0, it's 1 again. It's right there. When z is equal to 0, what's y?
1.
1. So it's right about there. So what do you do with this one? It goes below. And then what does it do? It goes above. What about this right here? When x is equal to 0, what's y? And I'll use a different color here, sorry. What color should I use here? There you go. When x is equal to 0, what's y? 1. So it's right there again, that point. And then when y is equal to 0, what's x?
Negative.
Oh, it's those 2 points again. So what do you do with those 2 points? Connect them. So do you see this plane right here? It's a little just in that quadrant. And what does this triangle do? It just expands. So the way you can graph planes, find out where the planes hit each axial plane, and they will hit each axial plane in a line, and then what do? You make a little triangle. So it looks like a little triangle meeting in a corner. But what does this thing actually do? Does it keep on expanding? Yeah. It's a triangle, but it keeps on going flat out on those lines. Yes, Craig? So let me show you a different one. Ready? 2x plus 3y plus 4z is equal to 12. When x is 0 and y is 0, what's z? 3. When you have, I don't know, 0, 0 like that, what's y? 4. And you have something 0, 0, what's that going to be?
6.
How many points do you have? 3 points. Are they all positive or all negative? They're all positive, so we have z, x, and y. So what do we have first? Z is what? 3? 4 and 6. What do you do with these 3 points? Connect them. And now what do we have? We have that part of the plane. We have that part of the plane. You graph lines like this. How many points do you need to graph a line? 2. 2. How many points do you need to graph a plane? 3. Any 3 points defines a unique plane. So if you can find 3 points, that's another way. And what are easy points to generally find?
And the other two is
Intercepts. Axial intercepts. If you find axial intercepts, you'll get this. But is that the only part of this plane? No. What does this plane do? It goes off in those directions. It goes off in those directions. Exactly. Last shape I want to show you, just quickly, this is the last small thing. What's the common thing between these two shapes? What's missing from here? What's missing from here? Z. Any equation where one of the variables is missing is called a cylinder. This is weird because you think of cylinders as one shape like this. This is a parabolic cylinder, and this is a circular cylinder. If a variable is missing, it's called a cylinder. I'm just telling you that because this is the case where the vocab is different all of a sudden. I know, you don't like that, okay? Your homework is listed I will put it up in Veracross momentarily, but I want to point out one thing for you. This is just to give you practice because we will do this in class. In your handout section, I gave you instructions for how to fold with paper a hyperbolic paraboloid. I just gave you instructions about how to fold with paper a hyperbolic paraboloid. Take a look at them if you want to. It's totally optional, but I'm going to teach you how to do this. See if you can get a little familiar before you come in.